before anything, let me tell you a story from ancient Greek mythology. This is the fight between Hercules and the Hydra of Lerna. Hercules committed a very serious sin. He was remorseful and felt a deep pain in his heart. So, to be forgiven and live in peace, he was ordered to complete 12 hard labors, of which killing the Hydra was only the second one. The Hydra had several heads and very strong regenerative powers, so that every time Hercules chopped off one of the Hydra's head, out of the wound, almost immediately one or more heads would appear. It was indeed really hard to kill the Hydra, but Iolaus, Hercules' nephew, found a workaround. Whenever a head was cut, using his torch, he would cauterize the wound, and that would prevent new heads from forming. So eventually, Hercules managed to slay the Hydra. I'm telling that story because it's the origin of the expression in Portuguese, bicho de sete cabeças. But not to be confused with the story of the seven-headed beast that appear in the last book of the Bible, the book of Revelations. I'm sorry, Bruce, this is another beast. Okay? The expression figuratively refers to hard problems with complex solutions like killing the Hydra, but is mostly used in negative form. Não é bicho de sete cabeças. It's not a seven-headed beast, to explain that certain things are not as complicated as they might seem. But I suppose the most common English expression that conveys the exact same message is, it's not rocket science. In this talk, I'm going to show you a problem and the solution that I came up with. And I hope to convince you that at least the problem não é bicho de sete cabeças, it's not a seven-headed beast, it's not rocket science. So thanks for attending my talk or for watching the video recording. I'm Cassio Neri. I'm a PhD in mathematics, former professor at university, but currently I work in finance in London. But this work here has nothing to do with my employer. I did that in my spare time. I'm here in a personal capacity, and all the opinions I'm going to express are my own. The problem we're interested in is the conversion from float point numbers to string, I'd say doubles. And here are 4 ways of doing that in standard C++. There are even more ways, but the point is there is more than one, and pay attention to the output is not always the same. And similarly, the same situation we found in other programming languages. And one reason for that is that there is no one solution fits all for this problem. Some users want more customability, other users want more performance, which brings our attention to chars and its output. So I'm going to show you chars is supposed to be the fastest, and I'm going to show what can run behind the scenes of chars and why it produces this particular output. So what's the deal, you might ask? We know computers store numbers in binary and we want to consume them in decimal. But we know how to convert from binary to decimal, right? It's just a bunch of divisions and modules operations by 10. In each step, we extract one digit, we convert to the char, so we assemble the string. Not a big deal, and here is the code that does that in that loop, 1 iteration per digit. Well, this problem is a very important problem. And this implementation here is just a textbook implementation. Some researchers, including Andrei Alexander's school, found sophisticated ways to improve the performance of this algorithm. So it is an important problem, but it's not the problem that we have now. Our problem is converting float point numbers, and here we are converting integers. Isn't that the same? Well, consider this number. The smallest is strict positive float. 2 negative 149. It's an awful number. It has 149 digits after the dot. So how we calculate this number? Should you run the loop that I just showed you 149 times? That sounds very slow. And besides, nobody wants to see that. We want to see something similar to that on the screen. But how do we get this number? Should we calculate the 149 and throw away most of them when we realize that there is one position 45 after the dot? That seems quite wasteful. So that's not the way. Actually, historically, at the very beginning was more or less like that they were doing. But nowadays, we have much better ways of getting this number here, and I'm going to show you. But before that, I need to do a quick recall on how float point numbers work, or more precisely, how they are stored and represented in bits. And I will start very slowly with a very simple CPU. A CPU that has just storage for 4 digits, okay? Think about the electricity or gas meters that you might have at home. But those electricity meters and gas meters, they show fractions. And here, our storage is just for integers. So fortunately, the mechanical engineers came up with a very interesting piece of technology to resolve this problem. Can you see it? It's very, very, very light here. Just a dot between the digits. And I put this gray out because it has no meaning with respect to the logic. It's just the same thing. The dot is just conceptual. It's there for us to see it, but it's not stored in any shape or form. It doesn't make any change to the logic of a simple counter. So now our storage for an integer number from 0 to 9,999 become a storage for a fractional point. And let's start counting. And you know where it's going, so let's speed up, and it goes up to 99.99. So one problem is fixed. From an integer representation, we have now a fixed point representation. But I'm not happy with the range. Almost 100 is not enough. I want a larger range. What can I do? Obviously, I can add extra digits, but that has extra costs. How can I improve the range, keeping the resource available? So one way of doing this is repurposing the first digit and look at it as the exponent in that expression. And again, everything that is gray, you might barely see it. It's there, it's conceptual. It's not stored in any shape or form. We still have our integer number stored. And the remaining digits are the so-called mantissa. And at the bottom, I'm showing you the corresponding fixed point notation for that expression. So let's start our counting. So there we are in steps of 0.01. We can increase, and let's speed up a little bit and make a pause here. If we keep the same logic as before, the next step, we will increment the exponent and reset the mantissa. But then we go back to 0. We don't want to go back to 0. We want to go to the next one, which will be 10. So we have to introduce a new rule here, which is this one on the top. Whenever the exponent is non-zero, that's the case, the mantissa first digit must be also non-zero. That's what we learn in school, we call that scientific notation, right? So let's keep our counting going on, and let's speed up and see. Look at the bottom. The numbers are increasing faster and faster, and the step between two consecutive numbers increase when the exponent grows, and we reach the upper bound of almost 10 billion. So not bad. Before was almost 100, now is almost 10 billion. That's much better, but I'm not happy with the small scale. The small scale, we start with steps of 0.01. What if I want more granularity, smaller steps at the very beginning? So I can rescale everything, and I'm happy to pay the price of losing the range a little bit. I don't need to go to almost 10 billion. So what we can do is we can just rescale everything, say by 10 to the negative 3, which is equivalent to moving the dot three positions to the left, okay? But moving the dot or moving the rescaling is equivalent to adding a bias to the exponent. So again, so we were here, so we just add this bias to the exponent. So let's start our counting, and you know what is going, and now, and etc. And okay, let's accelerate. That's it. We go up to almost 10 million, not 10 billion, but we start in steps of 10 to the minus 5 instead of 10 to the minus 3. So this is how float point numbers are stored in memory. But that's the decimal float point number, and computers are binary. So it's a bit different, but not much. So let's see the difference. The difference is now the base is 2 and not 10. And the exponent, the mantissa, and the bias here are now in binary. So these are bits, not digits. Just the 2 is a digit. Okay, and I'm not going to show you the fixed point notation. I'm going to place the number on the real line. So there you see 0. And let's start our counting in binary. No, sorry. Yes, so we are counting binary. And we make a pause here. Remember the rule that we had for decimals. It applies here with a little bit of a twist, which is this. So whenever we have a non-zero exponent, the mantissa first bit, not digit anymore, now is first bit, must be non-zero. But a bit that is non-zero, it has to be 1. So in a number in that form, it's so-called normal. It's a normal number as opposed to subnormal or denormalized number. And so normal numbers are to binary what scientific notation is to decimal. And let's keep going and look at the bottom, the position of the float point numbers on the real line. The steps between 2 consecutive ones is still increasing and grows when the exponent grows. And for the first one, for each exponent, I'm showing in a dashed green line, and that separates the float point numbers in 2 categories: the centered values and the uncentered values. The centered values are called like that because they are halfway between its 2 neighbors. Those uncentered values, they do not have this property. And this is relevant to us because most of the algorithms that convert from float point numbers to a string, they branch on whether the number is centered or not centered. So it's important to us. But most of them are centered numbers. So in this presentation, I'm going to focus the most common case, which are the centered values. So this is how float point numbers work. And the difference between different representations is mostly the number of bits used to store the mantissa, the exponent, and what is the value of the bias. And so then the IEEE standard comes in and defines these parameters for different float point representations. So they define the binary 32, which in C++ spells like float, binary 64 doubles, binary 128, your compiler might support that or not, and there are others, but are not that important for us for the time being. So let's see in more details the binary 32. Perhaps we should do the binary 64, which is the most common that use doubles and not floats, but they would not fit on my slide. That's why I'm using binary 32, but it's basically the same idea, it's just the number of bits that change. So the binary 32 format says that 23 bits must be reserved for the mantissa, 8 bits store the bias exponent, and 1 bit, I didn't mention before, there is a sign because obviously we want to work with positive and negative number. So let's see this bit pattern here and decode this number and see what it represents. So start with the sign. The rule is very simple. 0 means a plus, so we have a positive number. Then let's go to the bias exponent in binary. So the bias exponent is non-zero, so that's a normal number. And for a normal number, the IEEE standard says that the bias is 127, or this pattern 0 followed by 1s. So now, from the bias exponent, I subtract the bias, I get the unbiased exponent, just the exponent. So our number starts taking shape. Now the mantissa. So again, this is the bias exponent is non-zero, so this is a normal number. If it's a normal number, the mantissa first bit must be 1. And the remaining bits are those stored in memory or in the register. So this is it. That bit pattern represents this number here, which is still not very easy for us to understand because the exponent and the mantissa are in binary. Let's decimalize, then we can get a better feeling. So if you do that calculation, you'll see which number is that, but hold on, we will see in a detail. But now I want to mention the mantissa here. It's not an integer number. And for the sake of performance of the algorithms, it's better avoiding work with fractional numbers and work only with integer numbers. So we had this problem. Now we want to turn the mantissa into an integer number. What we can do is we can move the dot, the binary dot, one position to the right, which means double the mantissa, but you keep the same number, we decrease the exponent. We compensate the exponent. And we can do that again and again. Let me pause here. So we have 2 to the 0, which is 1, times this number here. So that bit pattern represents 10.75, which is still not an integer number. So, but we keep going, moving the dots, and now we have an integer number. But we have an integer number because everything on the right of the dot now is 0. If there was 1 somewhere, it will still not be an integer number. So to be sure that the mantissa will be an integer number, regardless of the input, we have to move the dots all the way to the right until here. Okay, now we are sure that regardless of the inputs, the mantissa will be an integer. So the takeaway from this slide is this. From this bit pattern, we extract 3 pieces of information: the sign, the exponent, and the mantissa of the binary representation. Keep that in mind. We'll use that later on. Now let's have a quiz. It's not a trick question, I promise. Or maybe it is. So I have a double variable x, which I initialize with 1 divided by 3, so 1/3. And then I ask the CPU to print this number. So here are 5 options. So please show of hands if you think that is going to print 0.3. Anyone? Nobody. Ah, I gave away the answer. Okay, you know that, okay? So the answer is 0.3333. And the difference with C is just the last digit, that's why I highlighted. D, I meant to say you would go to print 2 words, 1/3, and I gave you the opportunity to say none of the above will print something else. Okay, sorry for the spoiler. But here is another one. I will be careful now. Same thing, but with a float. The only difference is x is now a float. And the options are basically the same, but this float has less precision, so the output might have fewer digits. So now, let me be very careful and be away from that. Show of hands, who thinks going to be 0.3? Nobody. Option B, 0.33. Quite a few people. Option C. Wow, I'm surprised. Quite a few people as well. Option D, 1/3. Nobody. Something else. You guys are good. It's C. So that I think was halfway between B and halfway between C. So half of the audience might be surprised, as I was the first time I saw that. Why? Why this 4 here? I mean, it's not the way we would truncate this number. Would truncate like 3. And why is different from double? And so the confusion is because we are thinking like humans, we are thinking decimal. That's not how it works. So let's dig deeper and see why in this case here, it prints the 4. And by the way, same thing in other programming languages. That's not because C++ is weird. No, it happens also in other programming languages. So let's dig deeper this case here. So that's the number that I put on my source code, 1 divided by 3. That's what I typed, okay? So I put the decimal representation with the bar at the last digit saying it repeats. It's a repeating digit. So, and that number is 1/3, can also be represented like that. I leave you to prove that this number is indeed 1/3. It's a bit weird, but it will be clear why I'm doing that. So when the compiler sees the source code and see 1 divided by 3, it conceptually calculates this number here and they figure out that this number is between these two here. And these two numbers are representable as float point numbers. Nothing in between can be represented as a float, okay? So the compiler knows the CPU cannot store our 1/3, but the way I wrote it here shows that it's closer to the one at the top than to the one at the bottom. So that's why the compilers tell the CPU, please store that number at the top. So that's what the CPU stores. It's not 1/3. And then we ask CPU, please print the number that you stored. So what should be printed? First of all, forget the 1/3. The CPU never heard 1/3. The compiler told the CPU to store the number at the top. And besides, it cannot represent 1/3. So it's not going to be 1/3. All the CPU can take into account when it's going to print the number is the number it stores, and perhaps, and it does, take into account the neighbor. I'm showing you here just the previous float point number, but it also takes into account the next one outside of the slide, but I keep it simple, just see. So, and then the CPU is going to print something that can disambiguate between the number it stores and its neighbors. So how can it do that? Conceptually, it goes and it scans digit by digit until it finds a difference, something that disambiguates between the number it stores and the neighbor. And that's why it gets printed. I didn't put this display here, screen here, I put the printer, but it prints that number that we saw. So look, it's not 1/3, it's not the number that CPU stored, is yet another number, it's a third number. It's like we are playing the telephone game between ourselves, the compiler, the CPU, and the printer. If you do the same exercise with double, you'll figure out that there is a 3 at the end. It just happens like that. Okay, now it's time to see the dragons. The title of my talk is Another Dragon in the Dance, so I need to talk about the dragons then, but not the BBC TV program, these dragons then. I call the dragons then this list of algorithms that convert from float point numbers to a string. The first one, not really the first one, but the first one that had a precise statement of the problem they want to try to solve. It was not just print. Before was, let's print doubles. These guys, still and white, they came up. Okay, let's print doubles with these and these and these in mind. And they come up with one algorithm they call the dragon for some obscure reason. And they start the tradition of not everybody that follow the tradition, but some did. And they call their algorithms with dragon-related names. So some of them have dragon-related names. And here are some systems that use these algorithms. So as you can see, Grisu is very popular in browsers. And Ryu is used to implement two chars in the 3 main implementation of the C++ standard library. There is another dragon here, but that's another story you know better than me. And Dragonbox is used by the FMT library. And by far, Dragonbox is the most efficient of all. But there is a new dragon in the den. I will talk about this later on. But now let me take a step back and explain what exactly is the dragon's problem. So the algorithm to convert float point numbers to a string works in 3 steps. The first step is the decoding. It's something that we did before at that slide. So from the binary pattern, we extract the 3 fields. In particular, the exponent and the mantissa of the binary representation. Then we have to convert binary to decimal. It's something similar to what we did when we worked the example of 1/3, when the CPU had this number at the top of the blackboard, and then the dragon would output something similar to the one at the bottom. So that's the conversion from binary to decimal. And that is the dragon. That's the dragon's problem. But there is another step, after that, which is once we have the integer exponent and the integer mantissa, we run through this integer to a string conversion. So we convert the mantissa to a string, the exponent to a string. We assemble the string for the float point number. But the dragon, let me be clear, is the middle one. So all the papers that I showed before, all the authors, all the algorithms, they describe that step. Of course, the other two must be done by two chars and etc. But the dragon's problem is just this middle step here. Okay, that's what we are going to focus now. So giving a bit more precision, what we have is, we have an input which is of a number of the form mantissa times a power of 2, 2 to the e. That's the input, that's the binary representation of the number. And then Dragon must output a number of the form n times 10 to the f, so mantissa times a power of 10, that approximates the input. So, giving more precision, it needs to respect these 4 points in decreasing order of importance. There should be no information loss. It should be as short as possible, as close as possible to the input. And if these 3 things are not enough to decide what is the output, then some tie-break rules apply. Let's look a bit in detail each of these points. So first, no information loss. No information loss is playing the telephone game that succeeds, or the round trip, doing the round trip. But it has to start with the CPU, okay? There is no human involved anymore in this game. They exclude us from the telephone game. It starts with the CPU, and suppose the CPU store that number. We saw that example. So when I ask the CPU to print that number, it produces a string that is similar to that one here, okay? Now suppose a parser, could be the compiler or another parser, reads that string, conceptually calculate what that string, the number that string represents, but realize that the CPU cannot store that number. I cannot tell the CPU, please store that number. So the parser will tell the CPU to store another number. But if that number, we wish to have that this number that the parser will tell the CPU to store is exactly the number that the CPU had in the first place. So that's the round trip. That's the successful telephone game. But then there must be an agreement between the CPU and the parser. In the standard library, that agreement is the agreement between 2 chars and from chars. They apply the same rules. They talk the same language. So if you use 2 chars and from chars, you have the round trip safety. So how does the parser work? It's easier to understand the parser than the CPU in that case. So it's very simple. Here are 3 numbers in the neighborhood of the one we want to store. And the parser will calculate the number that reads and will tell the CPU to store one of these 3 that is closest as possible as the one that it just read. And it's easy to see that any number in this highlight interval is a possibility for the parser to, if the parser reads any number inside this interval, it will tell the CPU to store the number in the middle. So if the CPU wants to be sure of the round trip of the telephone game, when it produces the string, it must produce a string inside this interval, what I call the permissible interval. And there is a ambiguity when we are exactly halfway through 2 consecutive numbers. So then a tie-break rule applies, and the most common one, the one used by 2 chars and full chars, is round to even. So we prefer even mantissas, okay? That's the rule. There are other possible rules, but that's the most popular. Okay, so that's how the parser works, and because of that, the CPU must produce a number in the permissible interval to guarantee the round trip safety. Now, as short as possible, suppose the CPU will store the number on the left, so that's the input for the Dragon, and it might produce one of these 2 candidates output here. So which one should be? I'm saying that it should be as short as possible, but the 3 of them, they have 6 chars. So there is no one that is shorter than the other. But the rule is only the mantissa matters. Okay, so 1 has 1 digit, is shorter than 10, which has 2 digits. So that's why the dragon is going to produce the 1 at the bottom. One more example. This one here. So again, possible input for the dragon, 3 possible output for the corresponding input. So from what I just said, will tell me, okay, the dragon will give you this output, 1 times 10 to negative 1. But hold on, what about 0.1? It's the same number, but different representation. And it's indeed shorter than that 1. And in fact, that's what gets printed is 0.1. But remember, the dragon's problem is to find the decimal representation, a number of the form mantissa times a power of 10. So the dragon produced this one here, and after the dragon finishes its job, remember there is an extra step to convert integers when the input are the integer numbers, the exponent and the mantissa. At that time, the overall algorithm, not the dragon anymore, might decide, oh, hold on, for this particular number, the fixed point notation will be shorter. So it might fall back to the fixed point notation. But that's not the dragon's problem. Okay? The dragon's problem is to produce this output here. And there is another lesson from this slide. Notice that -1 is the largest exponent we have here. And 1 is the shorter mantissa. So the rule is the larger f, the shorter the mantissa. Larger the exponent, the shorter the mantissa. Keep that in mind. We are going to use that later on. One more example as short as possible. Why is that important to be short? So consider again, possible input for the dragon, 3 possible outputs for the dragon. The 3 outputs have exactly, the mantissa have exactly 8 digits. And there is no one that's shorter than the other. So perhaps we should, in that case, return the middle one, which is closer to the input. But hold on. This one here, obviously, is the mantissa is multiple of 10. So if it's multiple of 10, I can divide the mantissa by 10, and to not change the number, I can increment the exponent. The number stays the same, but now the mantissa is shorter. And actually, it's also multiple of 100 and 1,000, so on. So I can do that 7 times. So I can remove the trailing zeros, adjust the exponent, and now I have a mantissa has just 1 digit. It's very, very short. And why this obsession to be the shortest possible? That is a convenience for us. Because after the dragon produced these outputs, the remaining part of the algorithm will fall back to 0.3. And we humans, we prefer to see 0.3 instead of 0.300000001. Right? It's noise. We don't want to see that. So that's why Steele and White decide it should be short as possible for our convenience, for human. For the dragon is more work it has to do to remove this trailing zero. So that's for us. So that's the output of the dragon. So now, it's a dragon. I have to explain where this dragon, my dragon, comes from. So I will take Pythagoras' advice. Let's leave the roads of England and go to the trails of the South American forest. And let me introduce you to the Guarani people. Guarani people is an indigenous group of people from South America. And they live mostly what is now known as Brazil, Bolivia, Argentina, and mostly Paraguay. Actually, more than half of the population of Paraguay speaks Guarani as a mother tongue. Is one of the 2 official languages of the country with Spanish, and the Paraguayan currency is called the Guarani. So my dragon comes from the Guarani culture. So let me give you a crash course on Guarani mythology. But take everything I'm going to say with a pinch of salt. Obviously, I'm not an expert. I'm a quant. What do I know about that stuff, right? About that stuff. So, and even amongst the experts, there are disagreements. Overall, they agree, but are details here and there, so they have different accounts. I picked one account that I found beautiful, and I want to share with you. So, at the beginning, God Tupã and goddess Araçã, they create the first humans, Rupavê and Sipavê, the father of the people, the mother of the people. Tupã also creates two spirits, the good spirit, Angatuperu, and the spirit of evil, Taú. Rupavê and Sipavê, they have several children, including Marangatu, who was a beloved leader by his people, and he also had children, including the beautiful Keraná. Keraná means sleeping beauty, but there is no Disney involved. So Taú fell in love with Keraná and decided to kidnap Keraná. Angatuperu tried to avoid, they have a fight. Unfortunately, Taú won the fight and he managed to capture Keraná. But then goddess Araçã, she was really upset and placed a curse on Taú's 7 sons. They would be born as terrifying beasts. So the oldest one, the first one, was Tejú Jaguá, the first legendary monster of the Guaraní mythology, and my dragon is Tejú Jaguá. So my algorithm is named after Tejú Jaguá. He's the lord of the caves, protector of treasures, including the algorithm that he taught me. That's why I call it Tejú Jaguá. And despite his terrifying image, he's very docile. He doesn't make harm to humans. He eats fruits and honey, so he's vegetarian but not vegan. And so my algorithm is Tejú Jaguá. Let me show you how the algorithm works, finally. Still have some time. Good. So again, let's recall, we have an input with a number, m times the power of 2, 2 to the e, and we have to find an approximation of the form m times 10 to the f. And we are going to start our search by f. So here again, the real line, and I place our input at the center here. That's the number we have the input. We have to produce the output for that number. And we have to, and here are the neighboring float point numbers, and see that ours is exactly halfway between them, which means I'm assuming it's a centered value, not uncentered value. For uncentered value, it's a little bit different. Overall, it's more or less the same, but it's a little bit different. Let's focus on a centered value. And then we have to find an f such that there will be a possible output inside the permissible interval. And here are the extremes of the permissible interval. And this interval, we can figure out, it has length 2 to the e. This slide is getting too complicated for my taste. Let's simplify. All we need to do now is that we are searching for an f such that there will be a number of the form n times 10 to the f inside the permissible interval, and the permissible interval has length 2 to the e. Again, remember that rule, the larger the mantissa, the shorter, the larger the exponent, the shorter the mantissa. So we have an incentive to pick f as large as possible. But we must ensure that there will be a number of the form n times 10 to the f that falls inside the permissible interval. Otherwise, we have failed. So if we fail, it means that there is no number of that form inside the interval, but there is one that is before, and there is the first one that is after. And the difference between these two, because there are two consecutive numbers of the form n times 10 to the f, the difference between v and u will be 10 to the f. And in that case, because we fail, it's bigger than 2 to the e. So, if we fail, 10 to the f is bigger than 2 to the e. So to ensure that we don't fail, we enforce the opposite inequality. So we have to find a number f. F must verify that equality. 10 to the f must be less than or equal to 2 to the e. And f must be as large as possible. So it has to be the largest number that have this property. So f plus 1 must not verify this inequality. It must verify the opposite inequality. So we have these two inequalities for f. And if I take the logs, it means that e times log 2 is a number between two integers, f and f plus 1. So, in other words, f is the integer part of e times log 2. That's the definition of f. We have f. We have to carry on to find n now. But we must find 4 numbers. Bear with me. So here again, we have our inputs, the permissible interval, and its extremes. And as I said, we prefer work with integer numbers. And there are these halves here and there, they bother me. But we know how to convert, how to turn a mantissa into an integer number, right? We double the mantissa, we decrement the exponent. Now there is no half anymore. The mantissas are integer numbers. So we do this step. And we have to find a point of the form n times 10 to the f inside the permissible interval. So I'm denoting these points by a star. There also a star in the vicinity, but not inside the permissible interval. But by our choice of f, we are sure that at least one star will be inside the interval. There will be more, but at least one will be inside the interval. And I'm going to ask you to pay attention to 3 special star points. I should say a times 10 to the f should be less than or equal to the left extreme of the interval. But I will be abuse the language. I would just say a must be before or on the left extreme of the interval. Similar for b, must be before or on the right extreme of the interval. And similar for c, must be before or on our input. So let's consider these 3 numbers, a, b, c. Let's see how they are calculated. Start with a. So a is the largest that is before or on the permissible interval. So, sorry, the left extreme of the permissible interval. So a plus 1 must be bigger than the left extreme of the interval. So we have these 2 equalities here for a, which is a similar situation that we had for f, but now we'll just divide everything by 10 to the f. So it means that this number here is in between integers a and a plus 1, which means a is the integer part of this number here. So that's the definition of a. Same argument for b, but using the right extreme of the permissible interval, and same thing holds for c by using our input. So those are the definitions of a, b, c. There is one more number that we need to calculate to be able to decide what is the mantissa. So remember that when one of the star points, so I'm denote with big stars upside down, those that are inside the permissible interval. Our input need to be one of these big stars. And remember that one of these big stars has a mantissa that is a power of 10, sorry, it's a multiple of 10, then we can do better because we can remove trailing zeros and shorten the mantissa. So we have to ask ourselves if among the big stars, if they're one of that form, s times 10 to the f, where s is a multiple of 10. The best shot we have is this number here. Is a multiple of 10, is the largest multiple of 10 that is smaller than or equal to b. Because if it's bigger than that, so it will be outside the interval. If it's smaller than that, so if this one is not inside the interval, anything smaller than that will be also outside the interval, will be on the left. So that's our best shot. It's not guaranteed that we can return this one here, but that's the best shot. So we have A, B, C, S, and we have F. Now we can, in simple English, it tells what you should do. So you should return the shortest, which is S times 10 to the F, if you can, or if you cannot, if you must, then you return the closest, which you have the mantissa either C or C plus 1. And of course, so return the shortest if you can, or the closest if you must. And the shortest, when you are going to return the shortest, the S, you remove the trailing zeros before returning. That's what Tejú Jaguá does. Okay, that's what we should do. So, if you remember that sentence, the algorithm almost writes by itself. Let's see. So S times send to the F, I will denote with an I because we want to keep an eye on that point. And we are going to return that if that number is inside the permissible interval. Because if it's inside the interval, we can return that, and if we can, we do return that. But to decide if S is inside the permissible interval or not, we have to compare with A and B. So let's suppose that S is bigger than A and is smaller than B. In that case, we are sure that the S is inside the permissible interval. So in that case, we can return the shortest. If we can, we do return the shortest. What if S is not smaller than B? What if S, well, if it's not smaller than B, because it's smaller than or equal to B, if it's not smaller, it has to be equal to B. So it will be there, they are. Usually, B is inside the permissible interval, but there is a case. It could be that B is halfway between our input and the other input, the next float point number. In that case, S is a very good output for our number and for the next one. So both want to return S. So there is a tie. But if there is no tie, it means that B is not in the halfway, so it's inside the interval. So if there is no tie, we can return S, and if we can, we do return S. If there is a tie, then we have to run the tie break. And if our numbers wins the tie break against the one that comes after, the next float point numbers, then if our input wins, then we return the shortest. Otherwise, if none of these three last conditions hold, then we must return the closest, which is either C times 10 to the F or C plus 1 10 times to the F. Of course, there is more work to do here to decide which one is the closest. I'm sparing details. The slide suggests that in this case, C plus 1 will be the mantissa of the output, and Tejú Jaguá needs to do more work to figure that out. Okay, but that is still under the assumption that A is smaller than S. What if A is equal to S? So if S equals to A, usually A is outside the permissible interval, but we still have a chance when A is exactly halfway between our input and the previous float point number. Then A is a tie. So if it's a tie, but then we need to run the tie break, and if our mantissa wins the tie break against the previous float point number, then we can return the shortest. So if we can, we do. Otherwise, no chance, we must return the closer. That's it. That is Tejú Jaguá. When I derived this algorithm, my point was, I read the other papers. I didn't spend too much time, I confess, I didn't spend hours and hours and hours trying to understand, but I spent a fair amount of time trying to understand the other papers. And I found they were very complicated. So I said, can I do something simpler? I don't care about performance. I want something simpler. So I found that, and in my humble opinion, is much simpler. So I invite you to try to read the other papers and compare. I think this is the simplest I could get. But it turns out it's also faster. Sometimes those things come together, right? So, but before I show you, let me show you some hints why Tejú Jaguá is so fast. So some practicality. So I told you the definition of f is the integer part of e times log 2. And log 2 is this awful irrational number. Again, we prefer to work with integer numbers. So instead of using the 0.301 blah, 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 we find a rational approximation for that number, which has this huge numerator and the denominator is 2 to 32. So to calculate f, we just have to do a multiplication and a division by a power of 2, which means just a bit shift. Other algorithms also do that, but Tejú Jaguá goes further. If you were here last year and you watched my talk on current algorithms, you remember that a function of that form is an Euclidean fine functions, and I derive some properties of the functions, and Tejú Jaguá profit from these properties, the others don't. And it's important to say that this is an approximation. It doesn't work for any exponent. It works for these exponents in that interval here. But this interval is much larger than all the exponents covered by IEEE standard. So we are safe. And if it was not, we could increase the denominator, find another approximation for the log 2 with more bits, or instead of divide by 2 to 32, we could divide by, say, 2 to 64. That would be a workaround. But this is more than enough for all applications. Similarly, A has a formula like integer part of something. But that number that is multiplying the mantissa, the fraction there, is quite complicated. Look at the numerator, 2 to the e minus 1. That's an awful number, can be an awful number. Similar to the 2 to minus 149 that I showed you at the very beginning. So we don't want to calculate that at runtime. And actually, we can calculate this fraction and find another approximation for the fraction that is also has a power of 2 in the denominator. But the good news is we just need to do that once. We don't need to do that at runtime. There is one number, m of e, for each exponent. Actually, it's even better than that. There is one per f. But let's just assume one per e to keep simple. So we can put this m of e in a lookup table indexed by e. So at runtime, we just try to find m of e in this lookup table. It's just an array. And all the algorithms do something similar. And what is the value of k? So the rule of thumb is twice the size of the float point type. So for binary 32 floats, k should be 64. For binary 64 doubles, k should be 128. So that's how we calculate A, B, and also C is using this lookup table. Remember, we have to detect ties between possible outputs, if it's a good output for our number and the previous one or the next one. And detecting ties boils down mathematically to a divisibility check by 5 to f. And for that, Tejú Jaguá used the M-inverse algorithm. The other dragons don't use that, Tejú Jaguá does. Of course, I don't have time to explain the M-inverse algorithm, but if you look that up, you might find an article that I wrote in 2019 for overload, which I was very flattered was like the best article for overload that year. And so Tejú Jaguá used that algorithm. I told you C is calculated using something similar to A, but in some case, we can do something better. So there is an optimization for C. We don't need to do that calculation, which is among the most expensive that Tejú Jaguá does. There is also an optimization. It's a bitwise trick. I would not even say that it's Tejú Jaguá. It's something before Tejú Jaguá runs, it's detect. Is it a integer number? So this float point number actually represents a small integer number. If so, don't run the algorithm. Just do this bit trick here, is much faster. And Ryu also does the same trick. And there are all the tricks here in there, bit twiddling and etc. So now let me show you benchmarks. They are very boring, but they are very important. So here what I did was I took a large population of centered doubles and I run the three algorithms, Tejú Jaguá, Dragonbox, and Ryu, and I plot the histogram of time against the proportion of doubles that takes that time to be converted. So the more to the left, the faster is the algorithm. So you can see that Tejú Jaguá is on the left, followed by Dragonbox, and Ryu is much further down to the right. So Ryu is not really a competitor here. On the top, so among this population, what is the proportion of time that Tejú Jaguá was faster than Dragonbox? And that's 99.5% of the time. So there is 0.5% of the time where Dragonbox beats Tejú Jaguá. I don't know why. I didn't have time to dig deeper. And maybe if I do, I'll find, oh, I could optimize Tejú Jaguá in that point here and make it faster. But I don't care at this moment. My point is to keep it simple. If I have to add extra complexity to Tejú Jaguá for this 0.5% of the time, I'm not motivated to do that at the moment. Against Ryu, Tejú Jaguá and also Dragonbox beats Ryu 100% of the time. On the bottom, some statistics. Let's pay attention to here the last column is the relative average performance. So in average, Tejú Jaguá is 27% slower than, Dragonbox is 27% slower than Tejú, and Ryu is almost twice slower than Tejú. Okay, so to conclude, let's enter to the cave, because so far I have shown you Tejú Jaguá, the algorithm. I explained where it comes from, the culture it comes from, but I didn't show you Tejú Jaguá, the beast. So, ladies and gentlemen, it's my honor to present to you Tejú Jaguá. Any comment on his appearance? He's a seven-headed beast, but I told you I would try to convince you that at least the problem is not a seven-headed beast. The solution is a seven-headed beast, but it's not rocket science. Thank you very much for your attention.